All right, what's going on, chemistry students? So check this out. I actually did end up calling an anesthesiologist. He was actually a resident anesthesiologist over at UCLA. He's a teacher and he's also an anesthesiologist. And I asked him about the thing we were talking about on Monday, which was Bradley was saying, I'm not trying to call you out on this in no way, Bradley. I'm just letting you know that I was trying to do my research based off of the question you asked, and he was basically saying, "Why do I have to learn how to do this by hand? And also, what's the importance of this?" And in my conversation, I actually recorded it to YouTube, and I'll send you guys a transcript of it. But in my conversation with him, one of the things we talked about is we were talking about I asked him, do you have to dilute the medicine yourself, or does it all come pre-made for you? And the answer is, or at least what he said. Oh, okay. Here, let me explain to you what's going on in just a second. Let me tell you the story about the anesthesiologist right now. All right. So the answer that he said is different companies will send you different concentrations of the medicine. So you need to know how to combine them correctly in order to get the dosage that you're looking for. Additionally, if you need to dilute it for, like let's say you only have the regular human thing on hand, then if you need to dilute it even more than that, well, then you need to do like molarity conversions and stuff like that. And what he said, and I did ask him about stoichiometry specifically. I said, do you have to use stoichiometry in your everyday job? And he said, no, I don't have to use stoichiometry. And he said, I did have to use stoichiometry in the 4 chemistry classes that he had to take in order to get into med school, which is, 2 years more of chemistry than I even took. But he doesn't use it in his everyday work, Brad. And okay, yeah, he doesn't need it in his everyday thing. Another thing he said, and I thought this was really interesting, is he said we don't use a computer to do all of our calculations. A lot of times you do the hand calculations, especially if you need to do it really quickly. If you have an emergency coming in and you need to do a real quick calculation, you use your hand calculations as opposed to the computer calculations, which I thought was surprising because, to be honest with you, I would double check it with the computer. So what I guess my answer to you, Bradley, is from what I understand, from what I found out, it seems that he was really pushing this stoichiometry stuff. And feel free to talk to your friend, but that's what I found. Yeah, that surprises me too. It surprised me, and I was like, "Are you sure?" And I'll tell you what. I recorded the conversation. You can listen to it. I'll send you the link. All right. What happened to the homework? Well, we were not really grooving with this. We spent a lot of time on chapter 4. And it really just seems like you guys were, at this point, were like, man, this stoichiometry stuff is just ridiculously hard. Even though I just had a 5-minute conversation with you on the importance of stoichiometry. So my plan is to go on to, my plan is actually to go on to chapter 5 stuff. Cover that stuff, because the stuff in chapter 5 doesn't really require chapter 4 stoichiometry and balancing equations to deal with. It's almost a totally different part of chemistry. And then we'll come back to it after we've had a chance to digest it a little bit more. So I pushed chapter 4 homework that's due today till like 2 weeks from now. And I pushed up chapter 5 homework from being due next week to being due this week. So it's due like soon, tomorrow. What do you guys think about that? And I'll be honest with you, I really, really do think that chapter 5 is actually... What's up, dude? Come on in. What I said, Bradley, is I moved the chapter 4 stuff, the rest of the chapter 4 stuff, back 2 weeks from now, and I pushed up the chapter 5 stuff. My plan was to finish off chapter 4 today, but I decided, you know what? You guys have been butting your heads up against the stoichiometry stuff so much that I think that it's almost to the point where it's frustrating you, almost to the point where it's discouraging you. And I don't want to do that. I really don't. As a teacher, the worst thing I can do is discourage you and say, this is too hard, I'm going to give up. So what we're going to do is we're going to kind of move on to something different. It's not, I mean, I honestly think it's way easier. But then again, that isn't always true whenever I say it. Way easier for me is often sometimes like not easier for you.
Thanks for reassuring me.
Well, no, I thought that stoichiometry wasn't bad, but it turns out that it could be kind of bad for you guys. So what my plan is to move on to something else and then come back to it later after we've had a chance to kind of like calm down off of it.
Okay. I got 100 on the stoichiometry homework class.
Does that sound fair to you? So I pushed it back. I'm rearranging the chapters a little bit, and I'm going to kind of talk about something totally different. And we're talking about gas laws and pressure and that kind of stuff. And I feel like the way I can teach this one, I guess maybe I feel even more comfortable with it. And I think that's something I realized with when I was talking to Bradley. I was thinking like, you know, maybe stoichiometry is really important, and maybe your teacher just isn't teaching it to you very well, and that's why you guys are getting frustrated with it. You know what I mean? I think I'm doing a good job, but, you know, this is a tough subject. I feel like with gas laws, I can do even a better job because gas laws are also in physics pretty heavily. So, you know, it's a physics topic, it's a chemistry topic, it's really important stuff. Grab a chair, see if you guys can pull in.
Okay.
Just have a seat. And let's get this party started, shall we? What's going on, my chemistry students? Let's go with this thing. All right, let's see. So I think what I'm going to do is I'm just going to straight up start lecturing. And I apologize because I had this cool little Java script thing up and running for you. But the problem is the JavaScript's not running, so I'm not really happy with that. All right. What we're going to do is we're talking about gas laws. And we're talking about gases. A lot of what we're going to do today and, you know, the next chapter, you're going to have to kind of maybe, here, Emily, see how far you can come in.
Mm-hmm.
And
Batman Incorporated.
Huh?
Batman Incorporated.
Oh, you like that?
Yeah, man.
I was
really
reading
good.
the comic book.
I'm gonna go over the white.
I was reading the comic book and I didn't like it at all.
It gets better.
It was kind
You
of
gotta
bad.
get past the first. What? Do you just not like the suit?
No, I didn't like the writing. All right. Anyway,
Uh,
we're going to talk about gas laws, and gas laws. You're going to have to think a lot about. I find it's easiest when you think about being an individual particle of gas inside of a room. Okay, and I'm going to explain gas laws in that. But first thing I need to do is explain to you how we measure pressure. So pressure is a unit of measurement, right? And if you want to describe for me pressure, how would you describe pressure?
pressure.
Pressure is pressure?
Pressure's pressure. Yeah. it's
Pressure is pushing.
Pushing.
Okay? Justice is kind of pushing, and so, or Justin is kind of pushing, so you're saying pressure is pushing.
Like squatting too.
Yeah,
Yes.
okay. So, pressure is kind of like if you go deeper into a pool,
Yeah.
you
Your-
feel
your
more
ears.
pressure on your ears. It's pushing something in.
When
Okay.
I got to look at something.
All right, yeah. Pressure is kind of like, yeah, I would agree with that. Pressure is it's actually measured as force over area. So if it's a big force, then there's a lot of pressure. Or another way to increase the force is if it's a small area, then there's a lot of pressure. The reason why a needle hurts so bad when you poke it into yourself is not because the force is big, it's because the area that it's pushing on is so small. If I were to push with that same force with my finger instead of a needle, it wouldn't hurt at all. It would just be like, oh, you're pushing me. You're poking me, right? But if I were to
Yes.
poke you with a needle and I'm only pushing with a small force, a small force, but it's got an incredibly small area, then that pressure is huge. Does that make sense to you?
Yes.
There's one way that we measure
Whoa.
pressure, and it was done by this Italian scientist Evangelista Torricelli, who had been a student in Galileo. And what Torricelli did was they measured, Torricelli. They measured how far up. So they took a little container, and they filled it with mercury, and then they measured how far up the mercury went up into the glass tube that they put inside there. And they measured the height of it. And depending on that height, they said, at ground level, the measurement of this is actually 500, or no, it was actually, let's see. Yeah, it was 760 millimeters. That's an mm, by the way. I should maybe write that nicer. Millimeters. So at ground level, it was 760 millimeters. In fact, if I were to probably take one of these barometers, or these barometers, which was invented by Torricelli, it would measure, the glass tube, or the thing would go up into the glass tube 760 millimeters. Okay. If you're in the mountains, though, you guys ever drive up to the mountains?
Every day.
Well, I mean, to the mountains, not like mountains on Oahu. I'm talking about like mountains like Haleakala.
Oh
Yeah.
yeah, I went up there once.
Oh my gosh! Genesis, get your grandma to the emergency room. I'm so sorry.
Wait, what?
No, she just wrote. My grandma needs to be taken to the emergency room. Yeah, get out of here.
Sorry, need to go. Don't apologize.
Don't
for
even-
that.
don't even-
What? Holy, are you okay?
Look, we hope everything's okay.
I don't think she's.
Don't even respond. Get out of here. Get your grandma to the emergency room. I want to know if she's all right. All right. Yeah, it's not even funny. I don't understand.
What?
All right. Anyway, you guys ever go up into an airplane,
Yeah.
and then
Yeah.
what do you guys feel in your ears?
It's popping. Yeah.
It feels like pressure.
No, it's
It's
relieving
pushing
pressure.
in?
No, it's coming out.
It's pulling out.
popping. That's right.
Why is that?
Because there's less pressure, atmospheric pressure. No, there's more
Because there's less
stuff.
pressure up on top,
Yeah,
right?
Yeah.
And pressure is caused actually by the amount of air pushing down on your head. And when you go high up, there's less air above your head, between the atmosphere and your head.
I was reading something about this.
Does that make
Like
sense?
the exact weight of the air
So,
on top of your
so
head.
apparently, when Torricelli brought this little, pressure measuring tool up to the Boulder, Colorado, it only went up 520 millimeters. And why is that? Because there's less pressure. Right, there's less pressure pushing down. There's less pressure pushing down in this area over here, which means less amount of, which means this thing goes up higher inside of the little tube, or which means it goes up higher inside of the little, canister, and so it doesn't go up as high into the tube. Does that make sense?
So it's like when you check the pressure in your tires, you have that
There we go.
tool that you press.
Your little
it,
pressure
yeah,
gauge?
Yeah.
Okay, all right. So one way to measure pressure is using mercury. We often use mercury, and we often we often measure it in mmHg, millimeters millimeters of mercury. Hg is mercury, so it's millimeters of mercury.
Okay.
Regular pressure at the atmosphere is, 1 atmosphere worth of pressure, or the regular pressure at ocean level is equal to 760 mmHg. We also give that name we call it a torr. So I might switch between torr and mmHg, but really it's saying the same thing, because what we did was we made up a different unit and we named it after Torricelli. We said, hey, Torricelli was the first one to do it.
So
You
torr.
get the unit. So it's called a torr. Got it? So when I say torr, I really mean mmHg, which means millimeters of mercury, which means this is how far, like if I were to put this device in the inside of this pressure, this is how far up the tube it will go. Make sense?
Yes.
All right, good. Another way to measure pressure is in atmospheres. And this is actually the standard way. In fact, probably the way that most people in Hawaii, how much pressure we feel. We feel 1 atmosphere. Why is that? Well, because most people in Hawaii are at ocean level. And ocean level means there is, well, what's above your head? The atmosphere. How much of it is above your head? Exactly 1, atmosphere is above your head. So we say something at ocean level is 1 atmosphere of pressure. Whereas if we were to go down into the ocean, or let's say there was like a big hole in the earth, and we were to go twice as far down, then it would be 2 atmospheres, because there's 2 times the amount of atmosphere that's over your head. Or if we went up into an airplane and we were up here, how much pressure do you have? You have half of an atmosphere. Does that make sense to you?
Yeah.
Yes.
So there's different units, and one of the units we use is atmospheres. Another units we use is millimeters Hg, or torr. There's another weird one. Actually, it's not that weird. In physics, we measure force in newtons. And we also measure, so I told you pressure is equal to force over area. So we measure force in newtons, and we also measure area in meters squared. So we gave that a specific name. If you have 1 Newton per meter squared, it's called a Pascal, which is named after, I believe, this mathematician named Blaise Pascal. He's actually one of my favorite mathematicians almost of all time. Actually, of all time. Blaise Pascal. Awesome dude. Anyway, newtons per meter squared is the same as a Pascal, and 1 atmosphere is the same as 101,325 pascals. Why do we have so many ways to measure pressure? Well, it's because there's it was measured many times in history, and so we kind of have different, people with their different inputs on it. Plus, it's easy to measure things in atmospheres because it kind of makes sense intuitively. But, like 1 atmosphere, 2 atmospheres, those are pretty huge differences, right? So really what we say is it's actually, it's when you use different units, you can apply it to different things. Like I believe that the tire pressure that you were mentioning is in, I think it might either be I think it's pounds per inch squared, PSI, right? Pounds per square inch.
Yeah.
That's the same as pounds. Pounds is a measurement of force, lbs, and inches squared is how we would measure area in the dumb American units.
Yeah.
So we use PSI, so it's pounds per inches squared. By the way, 1 atmosphere is actually 14.7 lb per inch squared, pounds per inch squared, PSI. You guys want to know what the crazy thing about that is? What it's saying is if you were to take a quarter, which has maybe the area of an inch squared, right? About a quarter. And you were to put it on top of your head. Take a quarter and put it on top of your head. The amount of force that is pushing on that quarter is 14 pounds. That is what's pushing down. That is the amount of the air pushing on your head is pushing down with 14 pounds. Now, why doesn't your head crush in?
Well, ouch.
Well, the reason why your head doesn't crush in is because your head is hollow. Well, it's not really hollow.
Ouch, hey, got it. Watch it there.
Wow.
Well, the pressure is balanced in your head, so there's actually 14 pounds pushing up as well. So it's not basically going to break your head. But if you had a vacuum, like if I were to had if I had a vacuum, which basically means no pressure in the inside, and I were to push down with 14 pounds per square inch, that whole thing would crush. Like for example, and I think we'll probably crush cans in our next lab as
Crush
well.
cans?
Yeah.
Do you need your 5 cents back?
No, crush. We're gonna crush cans. We're gonna crush soda cans without stomping on them.
Oh.
We're just gonna throw them in water and they're gonna crush themselves.
What?
Yeah.
Really?
We'll probably
Science.
We'll probably crush cans without, without stomping on them. And the reason is because we're creating a vacuum inside, and then the atmospheric pressure is pushing down so hard on this thing that it's crushing these things.
That's awesome.
All right, so let me give you guys the units. You guys might need to write this down. And really, all I'm doing here is I'm introducing you to the different types of units, and you can use that now in your big conversion factors that we've been doing since the beginning of time. Okay? 1 atmosphere is the same as 760 mmHg, which is really the same as 760 torr. Got it? Which is the same as 101,325 pascals, which is the same as 14.7 psi, pounds per square inch, and that's the same as 29.92. There's one more unit I didn't measure, didn't explain to you, and actually once I write it down, it's self-explanatory. INHG. What do you think that stands for?
Inches of mercury.
Inches of mercury, right? Because like if we had millimeters per mercury, the English sure did want to, or the Americans sure did want to get their stupid unit in there. So they said, no, we're going to
Inches.
measure it in
That's
inches
inches.
per mercury, right?
Yeah.
Yeah. Hey,
Americans are stupid.
Yeah. Those crazy Americans, they're like, no, we can't do things in millimeters per mercury.
That's the
Or
measurement of
torrs.
freedom.
Yeah, we're measuring. Yeah, apparently United States and like Burma are the only free countries in the world.
Yeah.
They're the only ones who use English units. All right.
If you're free, you use inches.
So essentially, that's really it. That's that whole section right there. And all it is it's giving you guys some an arsenal of conversion factors. So if I told you, hey, I measure the pressure of something as 49 torr, what is that as measured in psi? Well, you can look up here at this huge equal sign
Just convert it.
and just say, all right, well, I know that I want to multiply it by some fraction. I know that the bottom wants to be torr. I know the top wants to be psi. And there is 760 torr is the same as 14.7 psi. So you multiply those two numbers, or those three numbers out, 49 times 14.7 divided by 760, and you end up getting, I don't know, whatever answer you get.
Maybe later.
Is that fair to you? Does that make sense to you? Is it easy enough?
Yes.
That's all that section is. Okay, so here's one of the things that I wanted to do a simulation, and the simulation will probably work on all of your computers, but it won't work on mine, which sucks because I wanted to show it to you guys. But let's go into this chapter, the next one. This is called the gas laws. Gas laws. So I'm going to show you 3 different gas laws made by Boyle, Charles, and Avogadro.
Not Avogadro.
Oh, good old Avogadro. I hated Avogadro. Yeah,
Uh,
same dude, avocado. Yep.
Not avocado.
All right, don't worry. I think in this one he's going to be a lot nicer to you guys than
Instead of
moles.
yeah.
It still is moles, but
No, it's not.
all right. Fine. It's coming back to moles, but at least we've seen it before, so it's not so freaky.
Oh man.
And don't worry about it so much. All right, don't freak out.
I can guarantee you it's still freaky.
All right. Okay. Check this out. Say I have a box, and I put some gas molecules inside here. And since they're gas molecules, they're not just hanging out there. what are they doing?
They're moving around.
They're moving around, right? All right. So they're moving all around. And I like what Bradley is saying. They're bouncing, right?
Yeah.
They're
So
bouncing.
They're in a box, right?
Right, they're in a box, and so they're moving, and they get to the end, they bounce. I would almost venture to say that I could define pressure as the amount of bouncing off the walls. Would you guys agree? It's almost like if there's high pressure, that means the gas molecules are bouncing more off the walls. They're hitting the walls more often.
That makes sense.
Does that make sense?
Yeah.
Whereas if there's low pressure, that means
They don't bounce.
they don't bounce as much. They're not hitting the walls as often. If I had some kind of counter and counted every single time they hit the walls, in a certain amount of time I would have less ticks for low pressure.
So
Okay.
high pressure is like a bunch of kids hopped up on coffee.
Yeah, exactly. In fact,
Oh my god.
In
You
fact-
just made that.
we're totally going to go with that.
Oh my god.
All right, so check this out. We're going to go with a bunch of kids
Oh my
hopped up
god.
on coffee in a heavy metal concert in a
Yes.
small room.
Yes.
All right.
In the mosh pit? Are they like mosh
In
pit?
the mosh
In the
pit.
oh my
So
goodness.
back
Yes.
when I was a kid, I actually used to play in a punk rock band, and I forgot
my
who
goodness.
asked me about Sublime, but someone was asking me about Sublime, like with Bradley Noel and stuff like that. And I actually played music with Sublime,
What?
With? As in.
on stage. Well, once on stage with him.
That's
Lucky.
amazing.
Yeah, well,
Dude, that's great.
I played in a rock band, and we were playing at Big Melee, and then Sublime was there, and there was that song "Wrong Way," and they had the
Oh,
trombone
dude.
solo.
Lucky.
And I had my trombone, and they're like, "We need a trombone solo." I was like, "I got it." I love Sublime. I know
That's
you.
amazing.
I know the thing. So anyway, all right.
Lucky you.
So we're at a rock concert, and I think a band that was really right. So don't worry, your teacher ended up becoming a total nerd
Thank
right
God.
after high school. Just like lost all of his cool points, became a physics nerd, and so. I still know what I'm talking about. I'm not as cool as I'm trying to make myself out to be. So I'm not even like trying to be cool at this point. I'm just like, I know I'm not going to be cool. I'm never cool. I've never was cool. Maybe I was cool back in high
You
school,
were
but not now.
cool when you played trumpet for
Yeah.
That was
That was
that's-
cool, but not
yeah,
now.
That's
All
a
right.
lot of cool points.
Yeah,
to
I'm
lose,
not.
man.
I'm not a cool surfer girl or a rock guitarist like you guys. Actually,
Yeah, what?
I do play a lot of guitar, but anyway, we're getting off topic. So let's talk about. Well, actually, the surfer girl is sitting right next to me. Her name is Emily, and she's awesome. Let's talk about being in a mosh pit, because I used to be in lots of mosh pits, and I don't know if you guys have any experience with being in mosh pits, or at least can you imagine being in a mosh
I
pit?
can imagine it.
Back when we used to play when we were in a mosh pit, right? And I think I went to Ozfest one time. Actually, I know I went to Ozfest. I went to Ozfest, so let's pretend I'm going to Oz. We're at Ozfest or a Metallica concert or whatever, and they're playing like their really popular song. Well, what happens is
The rhyme of the ancient marine.
what happens is you have your mosh pit and people are bouncing off of the ends, right? And you're getting hit,
Left
and
right.
then maybe we could say pressure is dependent on how often you get hit
Okay.
in a mosh pit, or how often
That's
you
it.
hit the sides of the wall,
Okay.
right?
Right.
That's
Or hit the side of the edges. How often you get thrown to the sides and then they push you back in the middle.
Does the amount of people in there?
So here's the thing. No, the number of people doesn't change. We're keeping the same amount of people in
Okay.
the mosh pit. But the thing is, when they play a really popular song, here's what ends up happening. The crowd behind you, which is usually all the people who are just watching the thing, they're not in the mosh pit. They're just watching. They're going,
Yeah.
"Ooh, let's go!"
And they're
right?
pushing you if you.
What happens is when they play a really popular song, here's what happens. The room gets smaller. Well, not the room, at least the mosh pit itself gets smaller because everyone just crowds in over here.
Yeah.
The hardcore people are still inside the middle and they're bouncing off the walls and like that. But and there's not any less of them. They're just
Just crammed up.
the space gets smaller.
Yes.
Do you guys agree?
I
Okay.
can confirm this.
So as your volume gets smaller, what happens to the pressure?
People are still going crazy in that.
Yeah, people go
They're,
super
they're not
crazy.
stopping.
Now, I know this analogy doesn't work completely because if they're playing a more popular song, usually you're moshing like even crazier, right?
Yes.
But let's pretend that we're not running faster or punching harder or whatever. we're still kind of bouncing off the walls with the same amount of energy. The problem is the volume, the room, the space that we have to dance in is much smaller. And I say dance with parentheses around it, or not parentheses, but the quotation, because moshing isn't really dancing.
You're dancing. What?
The
Right.
pressure increases.
Yeah, okay. The pressure increases. So as the volume decreases, your pressure increases. Do you guys agree?
Yes.
Okay. What happens if my volume increases? What happens to my pressure?
It decreases.
It decreases. So volume and pressure are inversely proportional to each other. If one goes up, the other goes down. And vice versa. If one goes down, the other goes up. So I could probably say something like P is, I'm going to write this funny symbol, and don't worry, this isn't a part of the math you need to know. I'm just going to put it here temporarily. P is proportional to 1 over V. And that funny looking symbol is actually an alpha in Greek. It actually just means, I used to call it a fish when I was a kid. It looks like a fish.
Yeah, it does.
It means proportional to, it means related to. Your P is related to 1 over V. Because the reason why I have the V in the denominator, because in this way, if the V gets big, then your P, if the number in the bottom gets big, what happens to the number overall? It goes
Would
down.
Get smaller. Yeah.
Right. So this is actually exactly showing you exactly what what we explained to each other in words. If V gets big, then P gets small. And vice versa, if V gets really small, what happens if your denominator gets smaller? Your number overall will get bigger. So this is,
Okay.
showing you this is actually the symbol for inversely proportional. Are we cool?
Yes.
Now, what we often do in science is we say, we don't like this inversely proportional thing, so we run a bunch of experiments, and we see, well, let's run a bunch of experiments, and let's see if this is the case. And what ended up happening was Robert Boyle ran a bunch of experiments, and he found something really interesting. And so, I guess the reason why I feel better about teaching this chapter is because, I don't know, to me it makes sense. As you kind of look at it, like, yeah, that makes sense.
Yeah.
Especially, maybe it's because I have so much experience in mosh pits.
That could be. Yeah. I'm finding that helped a lot actually.
Do you think that's... Because actually, we can ride that mosh pit wave to the end of this chapter.
Really?
Yeah.
Oh my goodness.
If we can imagine ourselves as...
Can we create a mosh pit?
No.
Well, because remember I talked about you want to envision yourself as a particle inside of the box. Well, essentially, being in a mosh pit is like being in a particle inside of a small confined box. So
Yes.
that's essentially what we're doing. All right. Anyway, here's what he found. He measured out the pressure, and he got that. He measured out the volume, and he got this. And the way he did this was he actually had a big glass tube in his house. And it was a curved tube. And then what he noticed is as he changed the pressure inside of here, the volume changed. Actually, the way he did it was as he changed the pressure outside of here, the volume changed. And so he measured, well, how does this pressure relate to the volume? So here's what he got. When he measured the pressure at 11, he got a volume of 12. Whereas when he measured a pressure of 29, he got a volume of 48. Which kind of makes sense because as your pressure got smaller, your volume got bigger.
Yes.
And you can see all of these numbers. But here's one of the really interesting things that he found. Is when he multiplied the pressure that he measured in inches of mercury, which I don't actually think he used inches of mercury. He probably used mmHg. I don't know why they were reporting it as inches of mercury, but whatever.
Because it's American.
Actually, was he American? He was an Irish chemist.
Well, is this textbook made? by
Whatever, yeah.
Americans?
This is an American textbook, so.
Yeah.
All right, when he multiplied his pressure times his volume, he ended up getting 14.1 times 10 squared. So, so 14.1. That would basically
That's-
be 1,410.
Okay.
He just got some number. But then when he multiplied 29.1 times 48, he ended up getting 14.0 times 10 squared. In fact, look at this. He multiplied all of these pressures times their corresponding volumes, and he got 14.1, 14.0, 14.1, 14.1, 14.1, 14.1, 14.0.
What?
Something is going on here.
Can confirm. Something is usually going on.
As he changes the pressure, the volume changes, and we were agreed with that. But when you multiply those two numbers together, they end up getting the same number. There's that number must be a magical number.
A magical.
Yeah.
Uh-oh.
So we end up saying something like this. By the way, I'm going to mess with my equation a little bit.
Okay.
I'm going to say P times V is proportional to 1. All I did was I just took my above
Yes.
equation and I multiplied both sides by V. You guys aren't freaked out by that, right?
Yeah, that's physical science.
And then what he ended up saying is, oh, wait a second. After doing a bunch of experiments, I can get rid of that proportional to, and I can say P times V is equal to K. And what is K, you asked? Well, K is apparently 14.01 times 10 to the square. Actually, it's not 14.0, it's 14.1.
I was totally hoping it was potassium.
No, it's lowercase k. It's K, which stands for constant. In fact, if we wanted to, we could call it Boyle's constant.
How does K relate to constant at all?
Because I don't want to use C because C was, reserved for light,
Okay.
right? E equals mc squared. You want to save C for something important like light. So we called it K. It's a constant. It's just a number. PV equals K. P times V equals K. We're cool with that?
Yes.
And apparently this thing is Boyle's constant. So let's see. How can we apply this to our lives now? All right, let's do an example problem. Okay, so I'm going to read the example problem. And sulfur dioxide, SO2, gas plays an essential role in the formation of acid rain. Awesome, acid rain, which is found in the exhaust of automobiles and power plants. Consider a 1.53 liter sample of gas at a pressure of 5.6 times 10 cubed pascals. So this is the volume, and here's the pressure. Agreed?
Agreed.
Okay. The pressure changes to 1.5 times 10 to the fourth power pascals. What is the new volume? So I'm gonna say maybe volume 1 and pressure 1, and I'm gonna say pressure 2 and volume 2, which basically just is saying that like I want to distinguish between the two, so I put a little subscript 1 and 2. So it's like before was part 1 and after is part 2. Does that make sense to you?
Yes.
All right. And according to my equation, P1 times V1 is equal to K, right?
Yes.
What about P2 times V2?
Equals K as well.
Equals to the same K. It's the same number, right?
Right.
It's a constant. So I could say that P1 V1 equals to P2 V2. Agreed?
If they both equal K, then yes.
Well, they're both equal to K.
So they both have to.
So then they're both equal to each other.
Right.
Okay. Now what did you want me to solve for? V2? What is the volume of my...
V2, yeah.
All right, fine. V2. So in order to solve for the volume, I'll just divide both sides by P2.
Get P1.
And that's it. So here's how I would tell you the volume. The volume is equal to 5.6 times 10 cubed pascals times 1.53 liters divided by 1.5 times 10 to the fourth power pascals.
Is that times?
All I did was I plugged in the numbers. I got my P1, V1, and P2 on the bottom.
Is that times 10 to the third?
Yes, that's times 10 to the third. Keep in mind that I'm writing on a computer screen, which is horrible handwriting. My handwriting is not really that bad. It's not really that much better, but I mean, it's not this bad. All right, use your calculators and have at it. Let's see.
I'll let someone else do it because my calculator is.
My calculator's on.
fine. What is 5.6 times 1.53 divided by 1.5?
Oh, that's
Somebody quick answer. I'm running out of thumbs.
All right, fine. Here, I'll guess the answer. How's that?
Okay.
I'll see if I can get close. I would say that this 1.53 is really close to that 1.5. So that cancels that.
okay.
Then I have 5.6 times 10 to the third divided by 10 to the fourth. So really, I have 5.6 times 10 to the negative 1.
What?
The 10 to the third on
Yes,
top
I can-
and the 10 to the fourth on the bottom. The fourth power wins by
Oh,
1.
Okay.
Okay.
So I have
Yeah.
10 to the negative 1. So I would say that my answer is 0.56 liters because the units of Pascals cancel out with the units of Pascals and my liters is left over. Make sense to you?
One. Yes.
Makes sense to me.
All right, apparently the answer in the textbook is 0.57 liters.
But because Mr. Delta is nice and he gives us, 0.1 margin.
Right. And the 0.1 margin on all of my homeworks will always give you, that will give you the correct answer.
Right.
Does this make sense as far as doing this? It's not that bad?
Not yet.
All right,
Oh,
cool.
yeah.
That's it for Boyle's Law. Let's move on to Charles' Law.
This is only one law.
That was Boyle's Law.
Yeah.
Well, Charles' Law isn't that bad either.
Okay, but when we get
All
to Avogadro's Law,
We're screwed.
it's all gonna
Yeah, I
it's
know.
like the floodgates come open.
Avogadro's Law is just
I know.
crazy. All
Raining
right,
fire on
okay.
the ungodly
let me see if I can explain Charles' Law. So, Charles' Law is a French scientist. His name is Jacques Charles. Actually, it's Jacques, which I'm sure is just Jacques. Jacques Charles.
It could just be Jake.
He's we'll call him J-Dog. Just,
There we go.
Just for us.
Nice. So we got
All right.
J-Dog.
So we got J-Dog Charles, or maybe just JC. JC. All right. So we got JC, a French physicist, who was the first person to fill up a balloon with hydrogen gas and fly solo in a balloon flight. Now we know now that that's not really a good idea after having the Hindenburg incident, but he did it and he ended up being alive. So okay,
Kind of got
Good for
whoop
him.
whoop-de doo for you. All right.
On a cookie.
Let's see if I can relate this back to the the mosh pit example. Let's go back to our mosh pit, and we got let's say a bunch of people inside of a room, or not a room, but
Pit.
a pit. And they're kind of. I draw the arrows, which basically means they're running and punching in that direction.
Yes.
And then they'll eventually hit each other or the walls and bounce off each other or the walls. Okay? And then let's say that they're playing, I don't know, what's like a pop punk band that you guys know nowadays? I don't know any music
We know
nowadays.
nowadays.
What's a
Well,
pop punk band that you guys
okay.
mosh pit to?
I personally go Dragon Force, but that's because I'm me.
All right.
And no one knows what Dragon Force is.
Are they like a poppy style
Taylor
punk?
Swift. Bradley, get out of here.
All right, fine.
You
Let's
know,
say-
don't use that.
Let's
Something
say
better. How about Fall Out Boy? They just
wait,
released
no,
a
no,
new
okay,
album.
wait, hey, let me finish. All right, so let's say you're at a Taylor Swift concert,
Oh my god.
and they're like, shake it off, and then you guys are
Bradley,
mosh pitting.
stop.
You guys are mosh pitting to Justin Bieber.
Oh my god.
Dude,
Alright.
that's my worst nightmare. That
Okay,
is my worst nightmare.
Yeah, I
So-
just peed myself a little bit.
so I'm gonna put Bieber up here.
Oh.
Beiber. Okay. All right. Now, what happens is you're at a Justin Bieber concert,
Bradley, what have you done?
and people are mosh pitting, and it's not really. It's kind of a lame mosh pit, right?
Ow, Bieber.
Yeah, like they're not really punching. They're kind of like, I don't know, like hugging almost, right? I know nothing about Justin Bieber. All right, but
Well, I think
Let's
you're
say-
nailing it on the head.
let's say that how's about let's go with good old Metallica.
Oh, yes.
The rhyme of the ancient mariner guy.
Good old Metallica comes on stage, kicks Justin Bieber in the head, and basically kicks them off stage and then starts playing their like super hardcore song. What's a really like to the bone like?
I'm telling you, Rhyme of the Ancient Mariner.
All right. Let's do that one. Okay. Just some kind of crazy like stuff. Yeah. No, not Demi Lovato.
Bradley,
Who said that?
get out of the chat. Bradley, go away.
I like Bradley.
Yeah,
All right.
these aren't.
So we have the same amount of people. We have the same room. But what's different?
Metallica guys are going crazy, and the Justin
Right,
Bieber guys are
right.
hugging each other.
Their arrows are like this, right? Like these guys are straight up like sprinting and knocking their heads against the wall.
Falcon
And then they're like
punch.
punching with a closed fist as opposed to an open hand punch. Yeah. As opposed to a little slap. Right? These guys are friggin' nuts. And they're just like, rah, right? They're just
Yeah.
going crazy
These
because
guys are Norwegian.
not only that, but they were at a Justin Bieber concert and then Metallica kicked Justin Bieber in the head. And so they were probably all angry too. Plus they're all amped up on the Metallica music. So what I'm doing here is
Sounds like the greatest concert
I
ever.
know. I know. So what I'm doing here is I'm increasing the energy. In essence, I would want to say that I'm increasing the temperature.
Okay.
And I think I made a mistake actually here. Let's say I'm increasing the temperature, but let's not make it inside of a room anymore. You're not inside of a concert room. We're still at a big concert where there's a bunch of people out here on the outside.
What about an outdoor concert?
Yeah, it's an outdoor concert, and the mosh pit kind of forms in the middle of the outdoor concert, and then you have a bunch of people around the outside,
Yeah.
right? And then so what we did was in the previous one, we had the people rush the stage, and so the mosh pit got smaller and confined, and it had to increase its pressure.
Yes.
Now this one, here's what I want to do is say that
I think
Say that- the people would bounce off the walls every so often here, right? And then say that in the when the Metallica comes on, what happens is they don't want the pressure to increase. They want the amount of times that they bounce off the walls to be the same, but these guys are running faster. What needs to happen? Does that kind of make sense to you?
What needs to happen?
What needs to happen if the guys in the Metallica concert are running faster, but they only want the people to hit the walls at the same consistency as in the Justin Bieber
Then
concert?
it needs to get bigger.
Ah,
It needs
that's
to get
good.
bigger.
There we go. What happens is these people need to back up. You just got to back up.
When you see guys like that at a Metallica concert, you do back up.
Yeah, and I agree.
Go ahead, stop that.
All right, see. But come on, you got to admit this is kind of a fun.
This is a
conversation.
fun conversation. I'm enjoying this.
What has to happen is if the Metallica guys go all crazy, right? They're all nuts, right? And you want people to, still hit each other just as often as they did just as often as they hit in the Justin Bieber concert. What happens is the mosh pit needs to back up
Yeah.
because those people in the middle are crazy. Does that make sense?
Yes.
And so they won't hit the walls as often because the room is bigger or the space amount they have is bigger. So tell me, as the temperature increases, what can you tell me about the volume?
Volume also increases.
Yes.
Yes.
As the temperature increases, in order to keep the pressure the same, the volume has to increase. Similarly, as the
Just
temperature,
like our mosh pit.
as the volume, yeah. If the volume were to decrease, okay,
Temperature would also decrease.
if the volume were to decrease, and I wanted to have them not hit as much, hit the same amount as often as they hit the walls. So I'm keeping the pressure the same, but if the volume decreased, that means they're going to have to walk or run slower.
Mhm.
That means they're not sprinting at each other; they're just kind of walking at each other, like the Justin Bieber concert.
Yes.
So
would I be able to say that volume is directly proportional to temperature? Right?
Yes.
Because as volume increased, temperature increased.
And as volume decreases,
As volume decreased, temperature
also
has to
decreases.
decrease in order to compensate so that it can keep that pressure the same.
Yeah, that makes sense. The mosh pit really helped, surprisingly.
Yeah, I know. Crazy,
Oh my
huh?
goodness.
All right. What Boyle ended up finding was he ended up doing the experiment, and then he ended up finding that, well, actually, volume is equal to B times T. And actually, this is Charles' law. Now, what is the B? Remember, back when we did Boyle's law, we ended up replacing this fish symbol with an equal symbol when we added in a constant. We said it's proportional to, but then after we did the experiment, we said, oh, it's not just proportional to, it's actually equal to a constant, K. Well, similarly, and this is what we do always a lot of times in science, is we say, well, volume is proportional to T, and then we do a bunch of experiments and we say, well, volume is actually equal to some other constant. Let's call this Charles constant.
B.
Which I have no idea why we use a B, but whatever.
Because
Because C
Well,
was reserved
C was
for
already
light.
reserved for light, so this is V is equal to B times T. Are we cool with that?
yes.
The last one, good old Avogadro.
Oh my goodness.
Oh my
God,
goodness.
stupid avocado.
Here comes the
Alright.
fire and sulfur on the ungodly sodomites.
All right, so I'm out of room. I'm out of space.
Oh, thank God.
Let's make a new document.
Oh man.
Did you forget he had a computer?
All right. Yeah, I know. It's-
He's out of space.
if the whiteboard's full, it doesn't mean. Oh, the whiteboard's full. End the class.
Oh, that means that we're done for the day.
No, that
guys.
just means I'm going to erase it and then move on to the next part. All right. So for Avogadro's law, here's what he figured out. All right. He said that say that we want to have the same temperature and the same pressure. Got it?
Yes.
But I have a concert. And this is all relating to like the same kind of thing where you have an outdoor concert with a bunch of people on the outside over here. Okay?
Mhm.
So this is all a bunch of people. And then here's the mosh pit in the middle. For those of you who, I don't know, for the other students, do you guys know what a mosh pit is? I'm just wondering. Like,
Look it up on YouTube.
Alana, I can't imagine you in a mosh pit. So
Thank you.
I don't know if you have experience with mosh pit.
The first thing that I'm proud of you for, Bradley.
And Bradley, have you been in a mosh
Like
pit?
the
Because
you just listed
I don't
Taylor
think they
Swift,
have
Bieber.
Demi Lovato in mosh pits. I don't think they have Demi Lovato mosh pits. Didn't
Bradley,
she
I
sing
think
Let It
you
Go?
may be confused here.
Anyway, if you look up what a mosh pit is on YouTube, I'm sure you'll find something.
We'll probably what the video is.
What was?
If you look up mosh pit in on YouTube, I bet that's what's gonna be
Justin, close
what's
the
going
door
on.
for me. He's too loud.
That's totally what it's gonna be. Some person filming in a mosh pit.
Yeah. Okay.
Okay.
I'm
You're
gonna
weird.
shoot you
Okay.
with a Nerf gun.
All right. So check this out. Here's the idea behind Avogadro's law. Say that we want to have these guys running, and it's a moderately cool mosh pit, right? They're not like super crazy running around, right? And we want to have them run at the same speed, so that means the temperature is the same. We want to have them hit the walls just as often. That means the pressure is the same.
Right.
But what we want to do is, that's scenario one. In scenario two, we want to add way more people.
Oh no.
We're gonna die.
So if that happens, because remember, Avogadro was a big fan of actually counting out the individual molecules. So he's talking about adding more particles of gas to the system. What needs to happen
They want to keep it.
If they want to keep the pressure the same, what needs to happen if you add more people to it?
Then
the volume needs to expand.
The volume, again, needs to expand. So you have a bigger area.
Temperature would also need to.
No, they want to keep the people running at the same
okay.
speed. So the volume needs to expand to compensate for the extra people. Does that make sense?
Yes.
So what he ended up finding was volume is proportional to N. And what does N stand for? N stands for number of molecules. And whenever we deal with number of molecules, you know that we're going to end up dealing with some kind of moles or something like that. But do you understand at least that? N proportional, or V proportional to N.
Yes.
And so we can end up doing that same trick that we have as V is equal to AN. Where A is what?
Avogadro.
A is Avogadro's
Finally.
constant. But it's not Avogadro's number, it's just some constant.
So,
It's just
okay.
some number that I can put in there that apparently this is all the same as. Does that make sense to you?
Yes.
Okay.
You're the only person I know that has a number named after them.
Well,
Anastasius.
yeah, one Anastasia. Apparently that's a revolution, huh? You guys are all into that?
Oh yeah.
Alright. Let's try this problem right here. I think this one's a good one.
That wasn't too hard.
Yeah, that wasn't too hard. I told you it wasn't that bad.
I was still freaked out when I heard Avogadro.
Alright, let's try this one. Because I didn't do an example on Charles' law, but I'll do an example on Avogadro's law. Charles' law is exactly the same. Essentially, let me go back to that example on Charles' law that I didn't end up doing.
We have a question. What does fish mean? Fish was constant, right?
Oh, the fish. No, it means related to.
Related to. So it just has something.
It's a
to do
math
with-
symbol that means, it actually means, technically the word is proportional to. Volume is proportional to the number of molecules in there, if you want to keep the temperature and the pressure the same.
Okay.
If the volume increases, your number of molecules is
So
going to have to
it's-
increase. And vice versa, if the volume decreases, your number of molecules, you're going to have less things inside there
Yes.
in order to keep the pressure and the temperature the same. Make sense?
Voila.
All right, good. And let's see. You know what's funny is I feel like the simulation actually shows you all of this stuff I'm talking to you about, but I almost feel like you guys are getting it more when we're just kind of imagining being at a rock concert. Or at least I feel like these guys over here
Yeah.
It makes more sense.
who are
We're
playing rock
cool.
bands. No, it's not that you guys are cool. I'm just saying. All right, whatever. All right. Suppose we have
Rebel.
a 12.2 liter sample of oxygen gas. So, sample containing 0.5 moles of oxygen gas. Got it? At a pressure of 1 atmosphere. Pressure is 1 atmosphere. And the temperature is 25 degrees Celsius. Oh, by the way, just to let you know, whenever you're dealing with temperature in any of these problems, it will only work if you convert everything to Kelvin. Okay? Converting to Kelvin is not hard at all. You want to know how to convert it to Kelvin?
Yes. You go to Google and you type in Celsius.
You
and
add
Kelvin.
273 to it.
Oh my! I actually knew
You
that.
just take the number, you add 273 to it, and that's it.
I totally remember that from
So
physical science.
25 plus 273.
Yeah, 25 plus 273 is what? 298?
I think we've had this conversation before.
Yes, we have. Yeah. When I taught you guys temperature and converting units and that kind of stuff. That was like from chapter 1.
Yeah,
Yeah, so
but
I
I still
forget.
think I wrote it down somewhere.
Yeah, all right. Anyway, you just add, you have to deal with things in Kelvin because that's the units to measure. If you deal with it in Celsius, it doesn't work as well. All right? Sometimes it works, but sometimes it doesn't work. All right, let's see. So hardcore because anyone can mosh pit at Metallica. Try mosh pit at Nick. I like Bradley. He's a
Bradley,
cool
that
guy.
was
Yeah.
okay. Bradley, I can forgive you.
Yeah, no, I mean, hey,
the previous comments.
If you can mosh pit, yeah, I agree with Bradley.
Metallica.
Anyone can mosh pit at Metallica.
But if you can
If you
mosh
can
pit
mosh
to
pit
like
at Demi
Nick-
Lovato,
Oh yeah.
that means you're a hardcore mosher. I agree. You know what? I take everything I said about you or previously back.
I
Brad.
take everything I thought about you back. How does that sound?
That's cool. All right. Anyway, so check this out. We want to, if all of this O2 was converted to ozone, O3, at the same temperature and pressure, what would the volume be? So we converted all of this O2, convert to O3. All right. So somehow we converted all of the oxygen into O3. We basically just added an extra O in there somehow.
Okay.
Got it? We have the number of moles, which is 0.5 moles of O2. We have the volume
Is that
initially, which is 12.2 liters of O2.
Yeah.
Whenever we're dealing with Avogadro's law, we keep the pressure and the temperature the same. Okay?
Okay.
Of the gas.
So it doesn't need that.
What we're looking for is we're looking for the new number of moles and the new volume. Actually, we're really just looking for the new number of moles, but we don't know what the new volume, but we don't know what the new number of moles is to begin with. So we're in trouble. All right. So how do we do this? All right. First, we need to, whenever we're dealing with moles and that kind of stuff, you need to have a balanced equation. Over here on this side, I have O2 gas.
So this is where
Over here on this
stoichiometry
side,
comes in.
I have O3 gas, right? This is oxygen, converts to ozone.
So
I'm going to
3
need
O2.
3 O2s and
And
2
2
O3s. 3 moles of oxygen, of regular oxygen, and will yield me 2 moles of O3 gas. Does that make sense?
Yes.
So here's my question to you is, how many moles of O3 gas do I have? Well,
You have 2 and
if I start off with 0.5 moles of O2 gas, once I have a balanced equation, which that is a balanced equation, I can convert moles of O2 to moles of O3. And what is that conversion factor? Well, it's 3 on the bottom and 2 on the top, because there's 3 here and 2 there.
Yes.
Warning, this is back with stoichiometry stuff. Is that hard? Are you freaking out, or is that all right?
Slowly getting it.
Alright.
Slowly.
Just letting you know that whenever we're converting and we're dealing with moles, we have to have a balanced equation, and everything has to be done in moles. Whenever we have a balanced equation, we're using some kind of stoichiometry of some sort. All right, but that's really it as far as stoichiometry goes. So now we know the number of moles of O3, but we want to figure out what the volume is. Okay, well, I told you that the volume is equal to A times N, right?
Mhm.
So I could say that the volume 1 over N1 is equal to A, correct? I could also say that the volume 2 over N2 is equal to A as well, right?
So volume 1 over volume N.
So I could say volume 1 over volume
N1.
N1 is equal to volume 2 over N2.
Yes.
And I want to figure out what volume 2 is.
It's just like what we just did in.
Right, but it's a little bit different. Because previously we had PV equals PV.
Yeah. But
This one we have V1 over N1 equals V2 over N2. So I want to figure out what V2 is, so I can simply say, well, V1 times N2 divided by N1 is equal to V2.
Yes.
All I did was I multiplied up the N2. And I know what N2 is. It's whatever this number is. And I know what N1 is. It's that number. Or it's this thing right here. And I know what V1 is. Shoot, I have all the information. I just
So
plug
all
it
we
in the
need
thing and
is-
calculate it out.
It's not too hard.
That's not too hard at all.
I can do some of
You
this.
end up getting 8.1 liters
So
after you've multiplied it all out.
N2 is the same as N1.
N2 is not the same as N1. N2 is N1 times 2/3.
Oh.
Yes.
Yes, and you can just plug everything in. You plug in 12.2 into here. You plug in whatever 0.5 times. Oh, can I plug it in? Oh, okay, fine. Let's see. 0.5 times 2/3 is the same as 0.33.
Well,
So, well, 2/3 is the same as once, or it's the same as 0.666666, right? 2/3 is the same as 0.66,
yes.
and half of that is just 0.33. That's why I got 0.33. Does that make sense?
Okay.
All right.
Makes
So what I'm multiplying is 12.2 liters times 0.33 moles over 0.5 moles. And then moles cancel out with moles, you end up getting liters, which is good because that's the units you want. Then you use a calculator and you end up getting 8.1. Does that make sense to you?
Yes. To me, Bradley, you good?
Okay, cool. All right. So, now what we're going to do is we're going to do something interesting. And I think that this one, I really like this. What we're done. Charles' law, or Boyle's law, not so bad. V is equal to K over P. Okay? Charles' law. V is equal to B times T. Remember we talked, all right, so for this one we talked about the mosh pit getting smaller, hence the pressure increasing.
Yes.
Or vice versa. The mosh pit getting bigger and the pressure decreasing. Right?
Yes.
For this one we talked about the mosh pit got more exciting and we kicked Justin Bieber in the head, and then the volume had to increase proportionally to adjust for the craziness that was going inside.
So when the temperature increases, the
No, we don't want the temperature to increase. Oh yeah,
when
since the temperature increased,
increase,
we don't want the pressure to increase,
Yeah.
so we had to adjust the volume to compensate.
Yes.
Fair enough?
Yes.
And then Avogadro's law was basically, I think it was V is equal to AN.
So more people get in.
More people get in, your volume has to compensate for that.
Yes.
What I'm going to do is I'm going to do a little bit funky. I'm going to go V over, or PV. Okay. You know what I'm going to do? I'm going to do this. PV equals K. V over T equals B. And I'm going to say V over N is equal to A.
Well, they're all. You can rearrange them all to find out whichever one.
Yeah, Alana, you can go. If I have a question. Yeah, okay, you can go. What did you say?
We learned about this in physical science. It's kind of like a triangle. You can solve for any single one of them by switching the equation around.
Okay.
So the first one would be V equals K divided by P. But say I wanted to solve for K, so I'd do V times P equals K, which is what we just did. If I wanted to do P, it would be, you know what I'm saying?
Yeah.
So that's not too difficult for me. Not yet.
I don't know. I think that I'm trying to figure out what I want to do with this. How I want to arrange this. I want to arrange this so I can combine them. I combine this information that I got.
Oh man.
Make just one huge equation.
Yeah.
Oh, I was joking about that.
Parentheses PV
Okay,
times parentheses
here's-
V over T.
Here's what I'm going to do. How's about this? Yeah, all right, here's what I'll do.
3V.
I'm going to say, but it doesn't really work as well. Okay, here, I guess I'll try it this way. P over T, no. I want to multiply K times B. That's PV squared over T.
There's an A.
Huh?
You're missing an A.
I just multiplied this times that.
Okay.
Let me think about how to do this correctly.
Ooh, that's confusing.
Yep. I just lost it.
Yeah, you're right. I don't want the square. I don't want the square at all. In fact, I really want to get rid of the K and B and A. I think that those are dumb.
Thank God my parents an eraser.
Okay, here. I'll do it like this. This will make sense. This will do it. Okay. I'm not going to solve for these things. I think that's a little too confusing. All right. What I did was notice how all of these are equal to V. Okay? So I could say something like this. V is proportional to, okay, P on the bottom, right?
Yes.
It's proportional to T on the top and N on the top. Do you guys agree?
So the volume is proportional to
It's proportional to P on the bottom. We know that from Boyle's law.
yes,
It's proportional to T on the top. We know that from Charles' law. And it's proportional to N on the top because we know that from Avogadro's law.
Then yes.
So there's three laws kind of going into this one thing. Volume is proportional to the temperature, the Avogadro, or the number of molecules, and the pressure, and inversely proportional to the pressure.
So it would make sense if it
Right?
was
Does that make sense?
proportional to all three combined.
So Bradley, did I answer your question? What all those stand for? I mean, those stand for the exact same things that we've been doing this whole time.
That makes sense.
And the trick that I've been using this entire time is I've been saying, well, I can replace this proportional if we do a bunch of experiments. I can replace this proportional to V is equal to some constant, which I'm going to call R. Yeah, P is pressure. So this R is actually a constant. In fact, there is a special name for it. It's called the universal gas constant, labeled R. I have no idea why it's labeled R, to be honest with you, but it just
It
is.
doesn't make
Couldn't it be G?
It could be G, but then again, we use G for gravity.
That's true.
So maybe R. I mean, we run out of alphabet.
whoever writes these things.
G
needs to be
squared.
fired.
I'll tell you what universal gas constant is equal to. You're going to have to look it up if you want to use it. It's 0.08206 liters atmosphere per Kelvin mole. That's the units on it.
That's kind of confusing.
It looks horrible.
It looks awful.
Actually, it makes perfect sense.
Stupid avocado with his moles.
Here's the way I never memorized this equation, the one I have written for you here. I'll show you the equation I memorized. I usually multiply P on both sides, and I end up getting PV equals nRT. I don't know why, but for some reason when I say it as pervnert,
Sounds like pervert.
Well, that would be why the class laughs at you when you say that. Okay, wasn't that
Bradley, the K over here is the unit
Charles.
of Kelvin, because we're talking about temperature, so it's
Oh.
Kelvin.
Oh, never mind.
Yeah.
I totally thought it was Charles.
No, that K over there is units, so it's actually measuring your temperature, which is in Kelvin.
So
No.
many Ks.
For some reason, I remember this equation whenever I think of the word pervnert, which is actually not a word either, but I thought it was funny. So PV equals nRT, pervnert. I don't know. Whenever I say that equation, that's just what I remember. That's just what I do.
So,
Yeah, seriously. No, seriously, I know it as pervnert. That's what I do.
oh my god.
And this is the ideal gas law.
Gas is so pervnerted.
Yeah. Gas is pretty pervnerted. Alright, anyway. No one else is laughing but us, so it might not be that funny. Alright.
Oh, I don't. Being that all three of us laughed,
Okay.
this is true.
All right. So I'll be honest with you. All of those other equations, the Boyle's law and Charles' law and Avogadro's law, you can now throw out the window.
Really? All we need to know. Okay, so what I just wrote down in my elaborate Google
So
Docs.
really, what you need to know is PV equals nRT.
Thanks, Donnie.
No. Well, I mean, you guys are all pissed off at me now, but I mean,
Since that's the important one, I'm gonna write it down in my alarm.
well, PV equals nRT. This is the equation to use. And why did I need to teach you all of the other gas laws?
So that we understand it.
Well, because they didn't come up with PV equals nRT to begin with. Boyle's law was invented in, let's see, Boyle's law, he came up with that stuff in 1627 or 1691, around there.
People are smart. Now.
Charles' law came up 100 years later, and Avogadro came up with his almost 100 years later after that.
What happened?
So this is over 300 years. They discovered these three different laws, and after the third guy discovered this third law, they were like, dude, wait a second. We can combine this into one big law called the ideal gas law.
Perv nerd.
Perv nerds.
That's
They all
amazing.
became a bunch of perv nerds.
Oh my goodness.
After 300 years, it took them.
It took them 300
Yeah.
years to become a bunch of perv nerds.
Yeah.
Yes, I know I'm abusing the word, and I'm saying it a lot just so I can get it inside of your head.
Perv nerd.
Perv
Won't
nerds.
ever-
Perv
Perv
nerds. All right. Anyway,
Perv nerd won't ever leave my brain.
Perv nerd.
I'll tell you why this is
You're such a
really.
perv nerd.
I'll tell you why this is really cool. And I ran out of room
You
again.
should go into class on Friday and start saying,
Oh, totally.
you're such a perv nerd.
Yeah, make it a thing.
We're gonna make it a thing.
Yeah.
And it's Anastasio is perv nerd.
PV equals nRT. No, don't make it a thing associated with it. PV equals nRT. What is our constant in this equation?
R.
It's R.
It's R.
So I could say PV over NT is equal to R. You guys see what I mean?
Yes.
And now after you look at this, you can say, oh, I see why the units. Look at what I wrote down for what R is. R is 0.08206. What is the units? Well, it's liters, atmospheres,
Over.
which is why it's volume, pressure, divided by Kelvin moles, temperature and moles.
Yes.
That's what R is. Okay, here's another thing. If R is constant, then I'm going to do that trick where I say, well, what about P1V1 over N1T1 is equal to what? It's equal to R.
R.
And it's also equal to P2V2 over N2V2.
If
Or
P,
T2.
If P2 N2 N2 V2 or T2 equals R.
Well, here's what we ended up saying. We ended up saying something like this. All right, this is true by the ideal gas law, right? And then we ended up saying that, like, if we don't add any more molecules to this thing, and we keep the temperature the same, that means N1 and N2 are the same, right? We didn't add any more molecules. So I can cancel those out. And T1 and T2 is the same. We kept the temperature the same.
Yes.
What is that? P1 V1 equals
P1.
P2 V2.
Yes.
That's Boyle's law. So then what if we go back to our crazy big equation and we say, well, we wanted to keep the volume, no, we wanted to keep the pressure the same and the number, I mean, obviously the number of stuff in there didn't change. So we wanted to keep the pressure the same. Look at that.
That's
That's Charles' law.
Charles. Oh my goodness.
And then we wanted to say something like, well, we want to keep the pressure and the temperature the same, but we want to change the number of stuff that's in there.
That's
Avogadro's
Avogadro's.
avocado law.
Oh my goodness.
So this ideal gas law kind of has everything inside of it.
That's incredible.
Okay. So here's a question that I can ask from the ideal gas law. And I'm just going to do this one example and then you guys are done. Get out of here.
Okay.
Which I don't think today's class was really that bad.
I think today's class was the best
Which
one yet.
I actually think that's your
Besides the
homework. To
s'mores.
be honest with you, I really think that your homework is actually very similar to this.
The one that I did yesterday after
No,
watching
the one that's because I took all of homework 4.
the.
I took the rest of homework 4 and I moved it. Demi Lovato is Demi Avocado. Yeah. All right.
Making ties.
We
guys.
have our own ways of memorizing these crazy things. But let me do an example for ideal gas law. I don't think it's that bad. A sample of hydrogen gas, which we can assume is about an ideal gas law, is a volume of 8.6 liters. So the volume is 8.56 liters.
Okay.
The temperature is 0 degrees Celsius. And what did I tell you to do? Oh, I don't know
Go
why I
ahead and
wrote that
convert
as...
it into Kelvin.
I have no idea why I wrote that as L.
Wait,
The
is this-
temperature is 0 degrees Celsius, which is actually 273.
Or is it
degrees
3 or
Kelvin.
5? I'm
273.
going to get it right one day.
The pressure is 1.5 atm,
Okay.
atmospheres. How many moles of gas is there?
We can,
And he was what?
we
So
can
here's
pretty
what
much,
you...
we can figure it out.
You know that pervnert,
Perv.
PV equals nRT.
Yes.
You want to solve for what?
Solving for
N.
R. No, solving for N. Sorry.
Okay.
We know what R is.
So apparently PV over RT is equal to N.
Yes.
So you plug P in here, you plug V in there, T in there, and you plug R in there, and you have your answer.
That's
That's it.
that's it.
That's
That's
it.
awesome.
Yeah.
I can do this.
Bradley will want me to do it, plug in the numbers, and I'll show you what I would do. I would just say N is equal to 1.5 ATM
Times
times
8.5.
the volume, which is 8.56 liters, divided by
1.5 ATM.
no, R, which is 0.08.
Oh, sorry. I thought
206?
that was
Was
zero.
it 206? Yeah. 206 atmosphere. Oh, no, wait, what was it? It was liters, atmospheres, Kelvin moles. Liters, atmospheres, Kelvin moles. And you want the temperature to be 273 Kelvin. Do you see why I can't use 0 degrees Celsius?
So will the
Because then I have
or-
0 in the denominator.
Yeah. Will
That
the
doesn't
R
make sense.
always stay the same?
The R is measured in this units. Well, here's what I'm going to say is I gave you the R in this units. If I were to give you the pressure in a different units like mmHg, then what you will want to do is you'll want to convert your pressure into atmospheres so you can plug it into an equation because you don't really want to look up a different R. That's a pain in the butt.
Yeah, I feel like.
But you can change the pressure that I give you if I gave you some kind of funky unit into atmospheres, and then you can now use it correctly.
Okay.
Same goes with if I gave it to you in milliliters, you'll want to convert that to liters because your R has a units of liters in it. Does that make
Right.
sense?
Yeah.
And you want obviously this liters cancel out with that liters, that Kelvin cancel out with that Kelvin, atmospheres cancel out with that atmospheres, and you end up getting 1 over moles as your units at least. 1 over moles is the same as moles.
Just 1 mole.
Yeah, it's just moles
Or
as your units. So if you use all the numbers and you take 1.5 times 8.56 divided by 0.80 or 0.08206, divide that by 273, you end up getting 0.57. So your answer is 0.57 moles. So apparently, if you have hydrogen gas at exactly this volume, temperature, and pressure, then you will have exactly almost half a mole. Exactly almost half a mole.
well, there it is.
That's it.
Is this being recorded?
This is recorded.
Okay, thank God.
I know. I'm definitely going back. It makes
Yeah.
sense. It
Yeah.
really does. Assuming that your calculations are correct, and that it is 5 or 0.57 moles.
Yes, assuming that I use the
Yeah,
calculator
yeah.
correctly,
Yes.
which I never use a calculator correctly because I don't even use a calculator.
You just use the book, or you just,
Well, I use the book, but a lot of times I just do it in my head.
that's a risky move there.
I'm not this smart yet, so.
All right, Bradley,
got
what's
one
your question?
Question time. The time we answer the
What bus are you catching?
questions. Probably 56.
Where are the problems for tomorrow's homework? Let's take a look at tomorrow's homework real quick.
Was it the one that I did and got 100 on?
I don't know.
I watched.
What are you talking
something
about
on-
tomorrow's homework? You talking about like the old tomorrow's homework or actual tomorrow's homework? Like what's due tomorrow?
I had trouble with
Oh, the pressure.
Pressure.
Oh, that's in chapter 5.
I didn't do that one yet.
Of course you didn't do it because I just switched it.
Well, thank you.
So chapter 5. Let's take a look at this. This
Homework
is due
5.1.
tomorrow. I'm just curious to know what it looks like.
Oh, it's only 5 questions.
Is it?
And you've given 5 attempts.
5 questions, 5 attempts, and what I'm asking you to do. Oh, whoa.
Number. What?
Sorry, I need to fix it a little bit.
Why is there a number sign, a pound sign there?
This is chapter 5, number 37A. You can't do the homework yet because I didn't put in the pictures for it.
What is a pound?
No, that just means I need to put in the pictures. What do you see?
A pound.
Yeah, that just means I need to go to chapter 5 and take problem 37A and put it into the thing for you.
Okay.
So you can't do this homework yet. I need to fix it for you.
I
I'm
need
sorry.
There was a homework from last week. It was one I talked to you about, the one I was struggling on Wednesday.
Yeah.
And I figured it out. I worked hard on it and dedicated myself to it. My piece of paper is like it multiplied into 5 pieces of paper.
Does that feel good to actually figure it out, though?
Yeah, it would, but now when I insert in the answers,
Alright.
I can't because the test is closed.
Really? That sucks.
Yeah, I'm
so
struggling.
sorry.
I'm struggling with the precipitation.
All right, so my answer for this one is I'll fix the homework and I'll make sure that you guys have it for by tomorrow.
I'm
sorry
struggling
about
with I'm struggling with the precipitation one.
Okay, wait. Let me stop the recording.
Bye, Bradley.